Chapter 5.3, Linear Programming. Many management decisions involving trying to optimize certain things like profit, revenue, and minimizing certain things like cost and materials involve linear programming. LP, as it is widely referred to, is a mathematical technique designed to help managers in planning and making decisions. It belongs to a broader field of mathematical programming. Programming refers to a modeling approach using systems of linear inequalities. Since we've already studied systems of linear inequalities, the algebra part of this should be just a review of a previous session. Basic assumptions. LP has been applied in many areas over the past 50 years. All linear programming problems have four common properties: maximizing or minimizing based on an objective, constraints that are introduced into the problem, and systems of linear inequalities. We assume certain conditions. First of all, we assume proportionality exists in the objective equation. We also assume additivity, divisibility, and the fact that the variables in the system are non-negative. Let's take a look at an example. The Flair Furniture Company. The Flair Furniture Company produces inexpensive tables and chairs. Processes are similar in that both require certain amounts of hours or man-hours of carpentry work and painting and varnishing. Each table requires 4 hours of carpentry and 2 hours of painting and varnishing, and each chair requires 3 hours of carpentry and 1 hour of painting and varnishing. There are at most 240 hours of carpentry available and at most 100 hours of painting and varnishing available. Notice that the words "at most" are important here because those quantities could be less than or equal to the quantities given. Each table will yield a profit of $70 and each chair will yield a profit of $50. Let's take a look at the arrangement of this information in the grid. Notice that carpentry and painting and varnishing are listed in the left column, while T for tables and C for chairs are listed in the vertical column. On the right hand side, notice that we have also listed the total hours that are available for each of the manufacturing processes. The object is to maximize profit. The constraints on the system are carpentry time 240 hours a week and painting and varnishing time 100 hours per week. The decision variables, T for the number of tables and C for the number of chairs. We're going to create linear programming objective equation first. We're going to hold on to that and think about that in the end. We're going to use this in order to determine how many of each should be manufactured in order to maximize our profit. So the maximum profit is going to be equal to 70T plus 50C. We have developed a mathematical relationship here based on the constraints. For carpentry, 4 hours per table times the number of tables plus 3 hours per chair times the number of chairs produced. The first inequality is going to be 4T plus 3C must be less than or equal to 240 hours. In a similar fashion, the painting and varnishing must be less than or equal to 100 hours, so therefore 2T plus 1C is less than or equal to 100. Both of these constraints restrict production capacity and affect total profit. The values for T and C must be non-negative, so it is implied in every linear programming problem that we do that these values must be greater than or equal to 0. In other words, they must be non-negative. The complete solution is that our objective equation, maximizing profit, is equal to 70T plus 50C, subject to the following. Carpentry constraint 4T plus 3C less than or equal to 240, 2T plus C less than or equal to 100, and both T and C must be greater than or equal to 0. Now, since we've already explored graphical techniques of linear inequality systems, you should graph these on the same grid, graphing each of the inequalities and identifying the shaded region for each one. We need to find a system that defines all of the solution region or the feasible region. Remember from our look at inequalities that the overlapping or final region is the feasible region, which must contain the solution that we're looking for. Take a look at the graph and the shaded feasible region. This is a closed feasible region, and we're going to take a look at a corner point approach. That means that we're going to find the corners of the region of feasibility. This can be done through algebra or can be done through a graphing calculator if you have one. Take a look at the four corners that we have found. The corner 0, 0, the corner 0, 80, the corner 50, 0, and the corner 30, 40. If we take each of those corners for T equals and C equals, and we substitute that into the objective equation, we get the following results: $0, $4,000, $3,500, and $4,100. Choosing the corner that produces the maximum profit here, which is the corner 30 and 40, tells us how many of each of those should be manufactured in order to maximize profit, and it also tells us that our maximum profit is $4,100. There are other techniques that can be used for multivariable systems. So in other words, when we have more than two variables in our system of inequalities, other methods will be introduced later on in other courses. This requires the use of software. Solving a minimization problem. Since our linear programming problems fall into two categories, either maximizing or minimizing, let's take a look at a minimizing problem. Most of the times we're trying to minimize cost, minimize labor in order to yield a solution to the problem. Let's take a look at the holiday meal turkey ranch, which is considering buying two different brands of turkey feed and blending them to make a food low-cost diet for its turkeys. We're going to let X of 1 equal to the number of pounds of brand 1 feed, and we're going to let X of 2 represent the number of pounds of brand 2 feed that are purchased. We're trying to minimize our cost, which is going to be in cents. That's going to be 2x1 plus 3x2, subject to the following constraints: that 5x sub 1 plus 10x sub 2 is greater than or equal to 90, that 4x sub 1 plus 3x sub 2 is greater than or equal to 48, and that 0.5x1 is greater than or equal to 1.5, and x1 is greater than 0, and x2 is greater than or equal to 0. These are the non-negativity constraints that are in all systems of linear inequalities that are used for linear programming purposes. Let's take a look at a breakdown. In the grid you can see that we have ingredient A, ingredient B, and ingredient C. Along the vertical columns, notice that we have brand 1 feed and brand 2 feed, and then on the right hand column we have minimum requirements. In other words, minimum monthly requirement per turkey. We also have listed on the bottom the cost per pound for each of the feeds: 2 cents for brand 1 feed and 3 cents for brand 2 feed. Using the corner point method, we construct the system of linear inequalities that represents this linear programming problem graphically, and we shade the solution region. Notice that we have an open region here, and we have 3 corners to identify: corner A, corner B, and corner C. We will solve the values either algebraically or by using a graphing calculator to identify the corners. Take a look at example 1. QM for Windows can also be used to solve this particular problem.